Hi there, and welcome to Chapter 2 in Stevens' Matrices, Vectors, and 3D Math. In this chapter, we're going to talk about vectors and the geometry of space. This particular video will cover Chapter 2.1, Vectors in the Plane. All right. And we actually covered vectors in our last chapter, right? Where we considered a vector was just, an array, either a column vector or a row vector of numbers, 1, -7, 3, or say 2, 5. And we could use these vectors to represent points in 2D or 3D. In this chapter, when we talk about vectors, we're actually talking about a single representation of infinitely many directed line segments. In other words, I can have suppose I'm in 2D and I have this vector, right? That's a directed line segment. That is equivalent to this vector and this vector and this vector and this vector. So a vector only has a direction and a magnitude, so it doesn't matter where it is. So it actually represents infinitely many directed line segments. If, however, you choose the original point to be 0, 0, then what that does is a vector then does in fact point to a specific place in 2D or 3D. So again, our vectors considered in this context can be used to describe points in 2 space and 3 space, and we can start talking about the geometry and manipulations in 2D and 3D. Okay, so I'm going to start chapter 2.1, but I'm going to switch into full screen mode. There we go. Okay, so vectors in the plane. So we start off with a directed line segment, right? A directed line segment has an initial point and a terminal point, and it's denoted PQ. So what I mean by that is if I have a point P here and a point Q here, that is a directed line segment. It has a length, right, denoted by these double absolute value signs, right? So the length is just double absolute value signs PQ, right? And we say that if two directed line segments or more, two or more directed line segments, if they have the same length and direction, they're called equivalent. So for any directed line segment, there are infinitely many equivalent directed line segments, right? There, right? And so what a vector is in this chapter is just the standardized representation of all these equivalent directed line segments, right? So this is a vector, this is the same vector, same vector, same vector. They can represent infinitely many equivalent directed line segments starting at one point and ending at another. Okay, so the component form of a vector looks like this. These are sort of triangular brackets, x, y, right? And you can think of this vector x, y as the vector that starts at 0, 0 and terminates at the point x, y. But the thing is, this same vector can be here, and so it won't point to the same place, or here, right? Or here. So it's written like this, but it won't always point to your location of interest because it doesn't necessarily start at the origin. But it does uniquely define that vector, which defines, infinitely many directed line segments. So for example, if I have a point P, that's my initial point, and a point Q, that's my terminal point, find the vector V, which is PQ. The way you do this is you just, it's defined right here. You take Q1 minus P1, comma, Q2 minus P2. In other words, I'm going to take, if I can erase that, That's going to be 4 minus negative 1, comma, negative 5 minus 3. So my vector v is just 5, negative 8. All right. So for notation, in the book, I'll generally be using boldface small letters, right? Unless I'm specifically referencing a vector with a given initial and terminal point. And you'll be using the sort of triangular brackets there. And the terms, if I have a small boldface u denoting the vector u, then the terms in that vector will generally be the same letter, non-bold, with an index indicating whether it's the first, second, or possibly third term when we get to 3D. Okay, and so equivalent vectors mean they have the same terms. Each term is the same, right? There's no ambiguity. It's the same thing as equivalent vectors from Chapter 1. Okay, so for an example, verify that the three vectors in the figure below are equivalent. Well, if you look at u, it starts at this point, terminates at this point. So the component form is 3 minus 1, comma, 6 minus 3. So it's 2, 3. If you look at this vector, starting at the origin, its component form is 2 minus 0, 3 minus 0, so it's 2, 3 as well. The component form of w is just 7 minus 5, comma, 4 minus 1, 2, 3. So all three of these vectors are equivalent. Right? They are the same vector. Right? They're equivalent, representing directed line segments with different initial points, really. Okay. So moving on. There's a few things I can do to vectors and some properties and operations. The first one is going to be scalar multiplication. And the way to think about that is if you have any vector like this, if you multiply it by 2, it gets twice as long. If you multiply it by 1/2, it's half as long. If you multiply it by, because I have my vector here, if that's u, then negative u looks just like u, only it points in the opposite direction. So that's another type of scalar multiple. It just switches the direction, but it gives it the same length. Parallel vectors. Two vectors are parallel if they are scalar multiples of each other. That means each term in v is the same multiple of the associated terms in u. For example, verify that u and v are parallel. Well, if you look at u, that's just 3 minus 1, 6 minus 3. So u is the vector in component form 2, 3. If you look at v, it's 6 minus 2, comma, 7 minus 1, 4, 6. And what you'll notice is if you take u and multiply it by 2, you get v. So v is 2 times u. They're scalar multiples of each other, and they're parallel. And the way you can check this, more suitable for checking with a machine, is you take this ratio, 4 over 2, compared to this ratio, 6 over 3. They are the same, and so you know that one is a multiple of the other. All right. Nice little trick for seeing if 3 points are collinear. The process goes like this. Suppose you have 3 points, P, Q, and R. All right. In this case, notice they're obviously collinear, or depicted as collinear. Here they are not. And the trick to determining whether 3 points is a little collision detection game, to determine whether or not these points lie in a line, is you just take the vector PQ and the vector PR, and it doesn't even matter which one you call P, so long as one of the points is the initial point for both vectors. If PQ and PR are parallel, that means one lies on top of the other. If PQ and PR are not parallel, they don't lie on top of each other, and the points are not collinear. So for example, verify that the points 1, 3, 5, 6, and 9, 9 are collinear. The way you do this is you look at, and you can use any one of these, but we'll start with P. PQ is just 5 minus 1, 4, 6 minus 3, 3, 4, 3. And then PR is 9 minus 1, 9 minus 3, so 8, 6. And if you look at this, if you take PQ, multiply it by 2, you get PR, and these vectors are parallel, which make these points collinear. And by the way, you could have checked just as easily QP and QR. All right, QP would have been, let's see, 1 minus 5, negative 4, 3 minus 6, negative 3, and QR would have been 9 minus 5, which is 4, 9 minus 6, which is 3. And you'd notice that QR is just negative 1 times QP. So QP and QR are parallel, and the points are collinear. So it doesn't matter which point you choose as the initial point, but it does have to be the initial point for both vectors. All right, vector addition. It's just like vector addition from chapter 1, but there is a geometric interpretation that is worth knowing about. Vector addition looks like this. Suppose you have U, by the way, it's just term by term addition. If this is U and this is V, then when you add them, you just add the first terms, add the second terms. So it's exactly the same as from chapter 1. But what it looks like, if this is U starting at the origin, terminating there, and this is V, you just go, you take the tip of U, connect the tail of V, all right, you get V there, and then when you connect the tail to the tip, you get U plus V, right? That's why it's called tip to tail, right? So you take the tip of U, attach the tail of V, and then where that terminates is U plus V. Now, vector subtraction, there's a name for this. You can go with something called tip to tip, but I actually have a preferred way to do this. I don't like subtraction. It doesn't commute. I prefer addition. So instead of doing U minus V, which by the way is just term by term subtraction, I prefer to do this. I prefer to do U plus negative V. Right? I like addition. What can I say? Can't mess it up as easily. So if I want to take U minus V, I first look at this. That's V, right? So minus V looks like that. Negative V. So then I just take U and then minus V, and then that is U plus minus V. U minus V. There's a tip to tip where you line up the tip from one tip to the other and then go tail to tail, but I prefer the U plus negative V. That way it makes total sense to me. I follow U, then I go negative V, and that's where I terminate, and that's U minus V. If you have a vector in component form that looks like V1, V2, the length of that vector is just Pythagorean's theorem. It's the first term squared plus the second term squared, square root. That's Pythagorean's theorem. If this terminates at this point, V1, V2, that means this distance here is V1. That means this distance here is V2. And this length of this hypotenuse is just V1 squared plus V2 squared, square root. All right. So for example, find the length of the vector from P to Q. Well, first thing I do is I get the component form of that vector. So that's 4 minus negative 1, comma 15 minus 3, or 5, 12. Square 5, square 12, add them, take the square root, 13. So the length of that vector is 13. Alright, how do I get a unit vector from a non-unit vector? And we do this a lot, so this is worth knowing. The definition of a unit vector is a vector with length 1. Right, so a lot of times we want to take a vector and find a similar vector with a different length. So the first thing you do with that is you actually give it length 1 and then multiply it by a specific value. So what we're going to do is called normalizing a vector. We take a vector and make it so it has length 1. All right? And we say this particular phrase. The unit vector, in this case u, in the direction of v is given by 1 over the size of v times v. All right? In other words, you take v, divide it by its length, or multiply by 1 over its length, and that's going to give you a length of 1. So u, the length of u, will equal 1. And u is often used to represent a unit vector just because it starts with the letter u. But not always. But you can take any vector and normalize it, meaning give it length 1. For example, find the unit vector u in the direction of v. Well, the first thing you do, here's the length of v. So it's negative 3 squared plus 2 squared, square root of 13. So the unit vector in the direction of v is just 1 over the square root of 13 times v. And you can distribute that through scalar multiplication. And if you were to check the length of this vector, you would get 1. All right. If you take it, let's just take a look. If you look at the size of u, just to confirm, that's going to be the square root of negative 3 over root 13 squared plus 2 over root 13 squared. And if you look at that negative 3 squared is 9, square root of 13 squared is 913, plus 413. So that's the square root of 13 over 13. So the size is 1. So it works. If you take a vector, divide by its length, that new vector will always have length 1. And so here's an application for this. Right? Suppose you have a point P and a point Q. And I want to find the point S so that S is on its way to Q from P a given distance. All right, what happens if I start at P, head towards Q, and go for 4 units? Where do I end? Right? And doing this, being able to normalize a vector, is critical in this step. So here's the strategy. I'm going to normalize PQ. I'm going to get it to have length 1. Then I'm going to multiply it by 4 so that this, so I'll start off with PQ. I'll normalize it so that it has length 1. But then I'll take this and I'll multiply it by 4, and that'll give me PS. And then I just take my point P, add the vector PS, and that'll terminate at S. All right? So that's what this is. And whenever I say add, I put a little double star there. Technically, you know, if you just listen to me carefully, I said you take the point P and you add the vector PS. Well, technically you can't really add a point to a vector, but if you throw them both in vector form, you can do so, and it serves a great purpose. So we will regularly be taking a point and adding a vector, even though you officially really can't do that mathematically speaking. Okay, so what is S? That's the question. What is S? So it's easy to do once you get used to the process. I first take PQ, right? And I know that PQ is 2, 3, 7, 12. So PQ is 7 minus 2, 12 minus 3. So that's PQ. The length of PQ is 5 squared, 9 squared, atom, square root, so it's the square root of 106, right? And so when I take that PQ, divide by its length, I get this vector u, right? It's not particularly pleasant, but what that vector is the point, not the point, it's the vector that starts at P, goes in this direction for 1 unit. That's u, right? Now I'm going to multiply it by 4. So that gives me the vector PS. And then S is just what happens when I take P, the point, and add it to PS. Right? Because if you think of P as a vector, I'm going to take P, add PS, that's going to end right here at S. Right? And when you do that, it's not particularly pleasant, and you really should have a calculator to get a feel for what that looks like. You get this value, 3.946.5. So if you try to do that with regular geometry, line geometry, that would be tricky. With vector mathematics, with vector addition, scalar multiplication, normalizing a vector, it becomes quite a simple task. Here's some properties of vectors and their operation of addition and scalar multiplication. Addition commutes, u plus v equals v plus u. They must be vectors of the same length. Associative, that means you can group the addition however you want. There is an additive identity. It is the 0 vector, and when you add that to any other vector, you get it back. You have an additive inverse. If you take u, multiply it by -1, add it to u, you get the 0 vector. Scalar multiplication is associative. You can take c times du or cd times u. You can distribute across vector addition, so you're distributing what is that? Scalar multiplication across regular addition. And you can also distribute scalar multiplication across vector addition. Right? If you multiply any vector by u, you get it back. If you multiply any vector by 0, it turns into the 0 vector. The length of k times a vector is just the magnitude, the absolute value of k, times the length of the original vector. Alright, the triangle inequality, it looks a little crazy, but it's called the triangle inequality for a reason. Suppose I have 2 vectors. Suppose this is u and this is v. If you take u plus v, then what you get is this vector u plus v. Right, u, v, and u plus v. We have a triangle there, right? And what we're saying is the length of any one side of a triangle is less than or equal to the sum of the lengths of the other 2 sides. Hence the name triangle inequality. Alright. Standard basis vectors, we call them I and J. You should recall those from chapter 1. We called it, let's see, E1, which was 1, 0, and E2, which was 0, 1. Those were in 2D. Alright, now we call them I and J, but they have the same vector representation. There's what I looks like. J looks like that. And any vector in component form can be expressed as a linear combination of I and J. For example, if I start off like this in component form, that can be written as u1 times I plus u2 times j. It is that simple. There's really no magic going on here. So if you're thinking to yourself, that's too easy, there must be more to it, there isn't. The component form, that's just called the horizontal. The first value, the first term in your component form is the horizontal component of u. The second term is called the vertical component. And if you want to make that sort of even more obvious, you could put it in terms of a linear combination of I and j. All right. So suppose I have this vector 2, 3. Express that as a linear combination of the standard unit vectors. That's just 2 times I plus 3 times j. Yes, it's that simple. All right. And finally, we're going to get into polar representation of a vector. Suppose you have a vector u, right, that is created by rotating theta degrees counterclockwise from the positive x-axis, and suppose it has a length given by that value, the size of u. All right, then that vector can be written in a couple ways. Here's the linear combination of the basis vectors. So that's the size of u times the cosine of theta times I, plus the size of u times sine of theta times j. Right? And those come straight from trig. Right? If you want this distance here, right, that is just this distance times the sine of theta. Right? And then if you want this distance here, that's just the length of this vector times the cosine of theta. So we can create these vectors if we know the angle with which the vector makes from the positive x-axis counterclockwise and its length. We can get the vector in this form, or if you want it in component form, you just take the length of u times cos theta sine theta. All right. For example, suppose the vector u has length 2 and makes an angle of 60 degrees with the positive x-axis. Express u as a linear combination of I and j, and then give the component form of u. All right, so I have the length of u, that's 2, that's easy enough. 60 degrees is pi over 3. And so as a linear combination of I and j, we're going to get a 2 there, a 2 there, cosine of pi over 3 there, cosine of pi over 3, sine of pi over 3 there. Now let's see, cosine of pi over 3 is just 1/2. So I get 2 times 1/2. Sine of pi over 3 is root 3 over 2. So I have 2 times root 3 over 2. So there I get 1. There I get root 3. So as a linear combination of I and j, I get 1 times I plus root 3 times j. And if I want that in component form, I just take the coefficient of I, which is 1, the coefficient of j, which is root 3, and the component form is 1 root 3. All right, so we can express vectors in component form as linear combinations of the basis vectors, and then you can even start off with a vector in terms of the angle it makes with the positive x-axis and how long it is. Now to actually operate with this, you'll probably need to take it from this form and convert it to one of the other two. So that is vectors in 2D. We'll get into vectors in 3D later. But so that wraps up the very first section of Chapter 2. And so I will see you in Chapter 2.1 if you are so inclined to keep going. Bye now.